Think about this. Every single day, you press a simple button on your computer, and within seconds, a flawless image appears on a piece of paper. You probably don't give it a second thought, assuming it's just cheap ink or some basic color dust inside a plastic shell. But here's what nobody tells you. That little cartridge sitting inside your office printer is actually one of the most volatile, dangerously complex, and tightly guarded secrets in modern engineering. In fact, if the microscopic powder inside that plastic casing isn't manufactured to a precision of less than 8 microns, it won't just blur your text. It can literally ignite into a floating fireball inside the machine. Imagine trying to control millions of microscopic, statically charged plastic beads, forcing them to move at lightning speeds across a rolling drum heated to nearly 200 degrees Celsius without melting into a smear disaster. Most people never think about this. But inside that cartridge lies a masterpiece of chemistry and automation that rivals aerospace engineering. We are talking about a multi-billion-dollar global supply chain that spans across deep underground mines in Africa, high-tech chemical reactors in Japan, and fully automated assembly lines that run 24 hours a day. Today, we are breaking past the security guards and the corporate non-disclosure agreements to take you on an exclusive, step-by-step journey through the intense heat, extreme pressure, and blinding speeds of the factory floor. But before we even touch the assembly line, we have to look at the raw ingredients. Because what happens at the very beginning of this process surprised even experienced engineers. You see, toner isn't ink at all. It is a highly specialized polymer plastic mixed with magnetic minerals, and sourcing these materials requires an unbelievable level of global coordination. If even a fraction of % of impurities sneaks into the raw material silos, the entire multi-million-dollar batch is instantly ruined. And this is where it gets truly extraordinary. The journey of a single cartridge begins thousands of feet below the Earth's surface, in a place you would least expect. To build the black heart of the toner, we travel first to the deep mining regions of South Africa and the oil refining capitals of the Middle East, where carbon black and specialized petroleum waxes are harvested. Carbon black provides that deep, rich midnight color, and it must be refined to a staggering 99.9% purity level before it is deemed safe for the factory. At the same time, massive ships transport raw iron ore from open-pit mines in Brazil across thousands of miles of ocean to specialized processing plants. Here, the ore is crushed and treated to create magnetite, a highly magnetic iron oxide that weighs exactly 45% of the final black toner formula. Meanwhile, the secret weapon of the modern toner cartridge, styrene acrylic copolymer resin, is being synthesized in high-tech chemical labs across Japan and Germany. This specific plastic resin acts as the glue, accounting for roughly 50% of 55% of the total mixture, and it is engineered to melt at a very precise temperature threshold. Think about the environmental footprint. Transporting these raw materials across 15,000 miles of global shipping lanes costs millions of dollars annually and requires massive energy consumption. But the real magic happens when these raw, unrefined elements finally arrive at the central manufacturing plant, ready to be subjected to brutal forces that change their chemical structure forever. Every single ingredient is meticulously weighed by computerized systems capable of measuring down to a single milligram, because a variance of just 0.1% can cause the toner to lose its electrical charge. The raw resin, carbon black, magnetite, and charge control agents are dumped into a colossal industrial blender known as a high-intensity mixer, spinning at an incredible 3,000 revolutions per minute. As the blades slice through the heavy powder for exactly 20 minutes, the friction causes the internal temperature to spike violently, filling the room with a deep, low-frequency hum. But as the raw powder blends into a perfectly uniform state, a sudden transformation takes place that catches the operators completely off guard, setting up a dangerous obstacle that the engineers must solve immediately. Once the raw powder is blended, it is fed directly into a massive twin-screw extruder machine, where the real mechanical violence begins. Inside this roaring steel chamber, the mixture is subjected to an intense temperature of exactly 140 degrees Celsius, or 284 degrees Fahrenheit, turning the dry powder into a thick, molten plastic paste. The twin screws turn at a precise speed of 400 revolutions per minute, forcing the viscous material through a narrow die plate under a crushing pressure of 5 bar, or roughly 72 psi. The smell of hot polymer and metallic heat fills the air as the machine pushes out a continuous, steaming ribbon of dark plastic that looks like a never-ending sheet of black lava. This molten ribbon can't stay hot for long, or the polymer chains will degrade and ruin the toner's future electrical properties. It is immediately pulled onto a high-speed cooling belt, where heavy, water-cooled steel rollers compress the hot plastic into a flat sheet just 2 millimeters thick while blasting it with freezing air. Within 30 seconds, the temperature plummets from 140 degrees Celsius down to a cool 20 degrees Celsius, causing flexible plastic to instantly freeze into an incredibly brittle, glass-like sheet. As it reaches the end of the belt, a mechanical hammer smashes down with immense force, shattering the brittle black sheet into coarse chunks the size of coins with a loud, metallic crunching sound. These coarse chunks are then vacuum sealed and sucked through heavy pipes into the most critical machine in the entire facility, the jet mill micronizer. Inside the specialized chamber, a hurricane of compressed air blasts the plastic chunks at supersonic speeds, forcing them to collide with each other at over 300 meters per second. The sound inside this room is a deafening, high-pitched scream as the chunks pulverize themselves into an ultra-fine powder with an average particle size at just 5 to 8 microns. To put that in perspective, a single human hair is about 70 microns wide, meaning these toner particles are nearly 10 times smaller than the finest hair on your head. But grinding the plastic to a microscopic size introduces a massive problem. If the particles are jagged and uneven, they won't flow smoothly through the cartridge, causing catastrophic paper jams. To fix this, the powder enters a thermal rounding chamber, where it is blasted with a brief flash of hot air at 250 degrees Celsius for just a fraction of a second. This microscopic burst of heat melts just the very outer edge of each particle, letting surface tension pull the jagged shapes into perfectly smooth, uniform spheres. The workers monitoring the control screens watch in real time as the jagged dust transforms into millions of perfect microscopic ball bearings, a process that must be executed perfectly because a single mistake here will lead to a chain reaction that completely shuts down the next phase of assembly. While the chemical toner powder is being perfected, a parallel line of heavy machinery is rapidly manufacturing the complex plastic housing that holds it all together. High-pressure injection molding machines, operating at a clamping force of 300 tons, inject molten polystyrene plastic into precision-carved steel molds at 220 degrees Celsius. Every 45 seconds, the mold is open, and robotic arms reach in to pull out the intricate, multi-chambered outer shells of the cartridges, producing over 1,200 units every single hour. The fresh plastic shells are still warm to the touch as they are placed onto a fast-moving conveyor belt, where they head toward a series of specialized subassembly stations. Now, the assembly line enters a cleanroom phase, where the cartridge is fitted with its most high-tech components, the organic photoconductor drum, or OPC drum, and the developer roller. The OPC drum is a seamless aluminum cylinder coated with a highly sensitive, green, or blue photoelectric polymer layer that is applied in a vacuum chamber down to a tolerance of just 0.1 microns. This drum is the heart of the printing process. It receives a laser beam from your printer, creating an invisible map of static electricity that attracts the toner powder. Mechanical arms press high-precision rubber sealing blades against the drum with an exact pressure of 1.2 bar to ensure not a single speck of powder leaks out into the printer's delicate laser gears. Next comes a filling stage, which is a marvel of dust-controlled automation, because floating toner dust can become highly explosive if exposed to a single static spark. The empty, sealed plastic housings move into an enclosed, negative-pressure filling chamber where automated nozzles drop down and pierce the fill hole of the cartridge. Using a specialized auger screw spinning at 150 revolutions per minute, the machine pumps exactly 250 grams of the microscopic toner powder into the cartridge in less than 3 seconds. The fill hole is instantly sealed using ultrasonic welding, a process where high-frequency vibrations at 20,000 hertz melt the plastic together without using any glue, creating a permanent, leak-proof bond that can withstand intense shipping vibrations. But filling the cartridge is only half the battle, because a modern toner cartridge cannot function without its digital brain. The smart microchip, robotic surface mount machines snap a tiny, gold-plated circuit board onto the exterior of the plastic housing at a blinding speed of 5 units per second. This microchip communicates directly with the printer, monitoring toner levels, tracking page counts, and regulating precise electrical voltage applied to the developer roller. But as the fully assembled cartridges emerge from the sealed cleanroom line, they face a brutal gauntlet of quality control tests where the slightest microscopic defect will lead to immediate destruction. Every single completed cartridge must pass through an automated quality control station powered by high-speed AI vision systems and laser scanners. These advanced sensors scan the exterior of the cartridge from 12 different angles, checking for structural microcracks or misaligned gears down to a tolerance of just 0.05 millimeters. If a single gear is warped by the width of a human red blood cell, the automated system fires a blast of compressed air, kicking the defective cartridge off the line and into a heavy recycling bin. Currently, the factory operates at a strict internal rejection rate of less than 0.3%, ensuring that only absolute perfection leaves the floor. To maintain international ISO 9001 and ISO 14001 certifications, random cartridges are pulled from the line every single hour and sent to a specialized stress testing laboratory. Here, a technician places a cartridge into an environmental chamber that simulates extreme global climates, baking the unit at 50 degrees Celsius with 80% humidity for 48 hours straight. Immediately after, the same cartridge is frozen down to minus 20 degrees Celsius to ensure the internal plastic seals and sensitive chemical powders do not crack or clump together. Once the temperature torture test is complete, the cartridge is slapped into a high-speed test printer that forces it to run at a blistering speed of 60 pages per minute, printing continuous high-density graphics until the reservoir is completely empty. Yet, despite all this incredible million-dollar automation, there is one critical moment where human skill completely beats the most advanced machines in the world. At the final inspection table, a master technician picks up every 10th cartridge, holding it up to a specialized high-intensity halogen light source to inspect the delicate surface of the green OPC drum. The human eye can detect a microscopic scratch or a tiny polymer pit that automated digital cameras occasionally miss due to light reflections. With a gentle, practiced flick of the wrist, the inspector spins the drive gear, feeling the resistance of the internal blades and listening closely to the quiet whisper of the moving parts, a level of sensory intuition that no robotic sensor can replicate. When you look at the sheer scale of this industry, the numbers are absolutely mind-boggling, representing a massive web of global commerce that keeps the modern world moving. Globally, factories produce over 500 million toner cartridges every single year, generating a staggering total market value of more than $5 billion. The production landscape is heavily concentrated, with Japan leading global manufacturing at 35%, followed closely by China at 30%, the United States at 15%, South Korea at 10%, and Germany rounding out the top 5 at 5%. This massive industrial machine employs more than 250,000 workers worldwide, from chemical engineers mixing polymers to assembly technicians managing the automated lines. To truly understand how far this technology has come, we have to look back 50 years ago to the early days of laser printing, when toner manufacturing was a completely different world. In the 1970s, toner was incredibly coarse, mixed in crude batches and poured into primitive machines that produced low-resolution, smudged text that looked terrible. Over the decades, the industry underwent a massive revolution, shifting from crude mechanical crushing to the high-tech chemical polymerization process we see today, allowing print resolutions to jump from 300 dpi to an incredible 1200 dpi. Looking forward over the next 10 years, future projections show a massive shift toward bio-based, soy resin polymers, and fully biodegradable cartridge shells as the industry races to eliminate plastic waste. Think about these 3 shocking facts that reveal the hidden reality of the device sitting on your desk right now. First, did you know that the speed of the toner powder inside a high-speed office printer can exceed 30 miles per hour as it flies across a static drum? Second, a single standard toner cartridge contains enough microengineered polymer powder to cover the surface area of an entire football field if you spread the particles out side by side. And finally, The static electricity used to pull the toner onto the paper is so powerful that it creates a localized electrical field up to 5 times stronger than the static charge that builds up on your clothes during a dry winter day. We have traced a journey from the deep, dark mineral mines of South Africa to the roaring high-temperature extruders and through the supersonic hurricanes of the jet milling chambers. We watched raw plastic and metal oxides transform into a microscopic, statically charged powder that behaves more like a liquid than a solid. It is an incredible, highly coordinated ballet of chemistry, physics, and mechanical engineering that happens completely out of sight, hidden inside a simple plastic shell that we completely take for granted every single day. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.